v equals, so the first term there gives us t equals minus rho of r and t over epsilon naught, right? And then we have a plus sign there, plus 1 over 4 pi epsilon naught prime to target over r c squared. But you can easily see from this, if you take the second time derivative, d2v over dt squared, let's just make it 1 over c squared along with that. So that is 1 over 4 pi epsilon naught c squared integral, so we have the second time derivative of whatever we're integrating here, rho of r prime gr over r prime. But, well, time would take the derivative with respect to time, just gives us a rho dot here. So just simply 1 over 4 pi epsilon naught integral rho dot r over r c squared in here. And that looks an awful lot like this thing. Bring this over to the other side. So this means what we have is minus rho r t over naught, and this gives us plus 2v over dt. And that is precisely what we wanted to show. So, nice. All right. So what we've done is from the ansatz that our potential of r and t is almost as in the static case, just the integral over charge distribution at the source. But the only difference that we take this retarded time, dr, r prime. So we have shown that if we calculate our potentials this way, then we are satisfied with this. So that means if we do it this way, we have calculated the potential properly in the Lorentz equation. And we can do the exact same thing. The proof is exactly the same, so we're not going to go through this again. We can do the same with the vector potential of r and t as being mu naught over 4 pi. Exactly the same, only that we take the current distributions in r prime gr. Good. Any questions? Problems? Is that going too fast? Too slow? So now if you go through this whole proof carefully, you can see, so now we have chosen the time at which we evaluate that as the retarded time as t minus distance over c. But you can also, the proof works exactly the same way if you take an advanced time. So Ta is t plus r over c. So in principle, the physics would actually, this would actually work the same way. If you say you don't see the source at an earlier time, you actually see the source at some time in the future. Which of course is physically nonsense, but mathematically this would actually still work, right? So this would be called advanced time. But again, even though mathematically that gives you a solution as well, it's clear that it's unphysical because you see something like travel time before it actually happens. So that can't be. So usually it's better to be advanced than retarded generally, but in this case actually you really want to be retarded instead of advanced. Good. Let's do one example that illustrates this a little bit. So that's the example 2. So the example, in that we have some wire going in the z direction, and we are located at some distance s perpendicular here. At some distance s from this wire. So for any point z along the axis, so let's call this the z, we have some distance r here, which is just given by r squared plus z squared, right? So there's no next charge here, so we have charge density always 0, but we're switching on the current at some point. So at some point there's the current I going here, the current I is 0 as long as the time at the wire is less than 0, and it's some I naught going in the z direction for retarded time greater than 0. So that means the current is on at some point s. We need to find the condition, so we calculate. So obviously, what is, start out with V, 1 over 4 pi epsilon naught rho r prime tr over r d r prime. What is the scalar potential? 0, right? Because we don't have any free charges, that gives us a 0 scalar potential in the Lorentz gauge. The vector potential A, we calculate mu naught over 4 pi integral, well, this is J, should actually write this as J. J somewhere on the wire at retarded time over R. Effectively, the volume where you have current is only on the z-axis, right? So we only need to integrate over that one dimension here. Okay, what is our retarded time? Our retarded time is the time in which we measure our potential here of R and T minus R over C, or that's T minus square root S squared plus Z squared over C. And so the integration gives us I naught, so something not 0, only for, so I at j not equal 0 for, well, tr greater 0. Right? So the integral goes only over the part along z where we see the current switch on. The idea being the further up you go in the wire, the further away you look, the earlier it is. Right? So there will be a time, even if we are at some positive time, there will be a time where you look so far back that you go below 0 with time. So you see only a finite section of the current being turned on. Okay, so we solve for this greater 0. So tr greater 0. Solve this here, that means that must be less than square root of ct squared minus s. Right? So that means you go, let's call this z naught. The integral where we actually get the contribution is from minus to plus this. 0. Beyond that, the retarded time is 0. You look too far into the past, so that the current isn't being switched on. Okay, good. So we can evaluate this integral now. So this a gives us mu naught. Wherever it's not 0, the current is I naught times z over 4 pi. You integrate only dz over r is square root s squared plus z squared from minus z naught to z naught. And that one can easily calculate, so you can look this up. I don't expect anybody to remember these kinds of integral, since there are sine hyperbolica, so you can write it in terms of a logarithm. So what we find is that this is mu naught, I naught in the z direction over 2 pi, and what is it, ln of some nasty function. Ct plus square root of ct squared minus s squared, right? Over s. Okay, this is our vector potential. I suggest we stay here. Everybody's done with this, and it's all in the book anyway. Then we can calculate electric and magnetic fields, and everybody, of course, remembers how you calculate the electric field and the magnetic field from the potentials. What's the electric field? Calculated from the potentials. Everybody knew that in the homework. For some mysterious reason. Second. Minus, sounds good. Gradient, yes, gradient B. That would be all for the static case, right? But for the dynamic case with time dependence, we have derived that there's a second term. Last week, right? Very good. dA over dt, yes. dt. And the magnetic field. Since its divergence is 0, we have said we can write this as curl of A, right? Okay, so let's calculate. V, so gradient V. So that means since V is 0, the gradient of course is 0 as well. So we just take the time derivative of this, and well, the time derivative gives you the ln, so 1 over that, then the inner derivative, you don't need to carry that through in detail, gives you, it's a minus sign here, minus mu naught I naught z times c over root 2 pi square root of ct squared minus squared. Okay, and the magnetic field B as the curl of A gives us curl, well, what comes in. So that's why I wrote this down here. We only have a z component, and that only depends on this perpendicular, this s variable, right? So we need to look for the z over the s here. V z over the s, I have that here, nice. There's no other term like that. So it is minus dA z over ds. And the phi direction, so we take the derivative with respect to s. Again, you can take a couple of lines, we don't need to do this here. It gives us mu naught I over it's 2 pi s, right? 2 pi s, and we have ct over square root of ct squared minus s. Okay, so we have our electric and magnetic fields from that configuration. Which is, in a sense, first maybe counterintuitive. If you have no charge here, only a current going through, you have a wire there, a current, you don't usually feel an electric field, right? That's only because this is time dependent. The wires, the charge is, that the current is only switched on at a certain time. So as you look back, as time goes on, we see a larger and larger fraction of the wire actually filled with currents. So it's only that time dependence that actually gives you this electric field, not zero. But if we go to a static situation now, so if we leave the wire on forever, and so look back at this 100 years from now, so if we take the time to infinity, then of course this, the time to infinity, what happens to the electric field if you let the time go to infinity? Goes to zero, right? That's what you expect. If there's just a wire and nothing is changing anymore over time, then there's no electric field. It's only while you see it being switched on, then there's a time dependence. That gives you the electric field. And here, if we take time to infinity, then the ct here will dominate over the s. Just take the square root, get ct over ct. The whole thing does, by the way, I forgot the phi. This whole thing just becomes 1. So it goes to mu naught I over 2 pi s to the phi direction. Which is also what you know classically. If you have a wire, you see a magnetic field curling around it, right? So in the phi direction. Okay, good. You can. Let's see. Let's leave this here because we will come back to this example after the next step. Okay, now go on one step and ask if one can calculate the fields maybe directly from the current and charges. What we've done for the example here now is to use our general solution for the potentials, use the potentials to calculate the fields. Maybe we can skip that step and use the charges and currents directly to calculate the electric and magnetic fields. So let's see if we can do this directly with our expressions for B and A. So let's calculate what is the electric field. The electric field, of course, minus gradient V minus dA over dt. Well, that's pretty easy. Gradient V, that's why I left this here. We've already done that. So this is 1 over 4 pi epsilon naught integral. So we integrate over all r prime. We have minus rho of r prime tr over r squared minus rho dot of r prime tr over c, right? Then in r direction here. And then let's see what's the last term is here. dA over dt is mu naught over 4 pi integral d3 r prime. Well, this would be, if we want to take the derivative of that, j of r tr over r, right? So this simply just gives us a j dot here. So the time derivative gives us a time derivative there. And to kind of write this in the same integral, let me add epsilon naught on both sides, and mu naught epsilon naught is 1 over c squared. Right, so now we can put that in the same integral here with a minus sign. By the way, I made a sign error here. Anybody see where? E is minus gradient V. Gradient V has the minus signs here. So we will actually come in with a plus sign. Minus dA over dt gives us a minus dot of r tr over r c squared. Okay, this is the expression for the electric field. And wondering, the magnetic field may take a few minutes. That goes into coffee break time. Maybe just to say the equations that we're getting here for E and B, which we will calculate after coffee break. Curl of A equals, so we will do that in a minute. These equations are called G-field-Poles equations. This will only take more than 5 minutes, so I'd suggest we break for coffee now. Is there any questions? If not,